back to the computational method on the optimization in this class, and we will talk about the conjugate gradient methods. And we will divide it into 2 or 3 classes. And first we will introduce the linear conjugate gradient method and the conjugate direction method. And then we will discuss the nonlinear one. Okay, this conjugate gradient method can also solve the nonlinear optimization problems. And then we will discuss the relation between the conjugate gradient method and the quasi-Newton method, and some very recent but efficient modification or variants of conjugate gradient method. Okay, but in this class we will talk about the linear one and with classical result. Okay, so first let's review our problems. We want to solve the linear system. Okay, the linear system is a typical large or sparse matrix. Actually, when this A is the size, the dimension of the problem is not so big, is a smaller one, you can use a direct method. Okay, like the LU decomposition. You use this, you get the solution directly. It is accurate and robust, but the computation is very expensive. The complexity is the O is n to the power of 3. Okay, and for the sparse matrix with yield condition, the memory increase a lot. Okay, you requires a lot of memory to restore your variable, and not feasible for the large scale problems. Okay, for example, when the n is larger than 10 to the power of 5, maybe nowadays it's better than before because of the development of computers, but it's still not a good method for large problems. Okay, and the next one, when the problem became larger, you can also use the iterative method like the Gauss-Seidel, okay, which is much cheaper in each iteration, but the convergence of this Gauss-Seidel is not so good, and it's not very easy to do the parallel computation via this Gauss-Seidel computation. And also it is not so efficient for the large-scale large-scale problems, especially in the machine learning and artificial intelligence. So we want an iterative method which is cheaper and also can converge faster. Okay, it's a scalable for the large sparse system and inexpensive for each iteration and converge rapidly, and it can be parallelizable, and this will lead us to the conjugate gradient method. Okay, but before we go to the conjugate gradient method, we will discuss about the conjugate direction method, which is a more general framework, and the conjugate gradient is a special case of this method. Okay, so before we go to the method, we will introduce some preliminary result. The first is exact length search. Let's recall what we have discussed about the length search in the gradient descent method. Okay, actually we didn't introduce any exact one. We just introduced like Armidjo line search, okay, or Armidjo condition. Armidjo condition with backtracking, or like the Wolf condition of the Wolf line search we have introduced and used for the BFGS, okay, for the quasi-Newton method, which can guarantee your direction is a descent direction for the quasi-Newton method. And there are also some other inexact line search conditions. But in this class, we will use exact length search, which means, for example, we consider this unconstrained optimization problems, and we use this length search scheme. So how do we get the next point? We began from xk, we find some direction, which usually is a descent direction, and some proper step size. Okay, so we define this phi alpha, okay, which describe or mirrors the increment of the function value. So what is the exact length search? It means we choose alpha, which is argmin of this phi alpha. For all alpha is greater than 0. Okay? So this means we do one dimension minimization along the direction decay. Okay? Along this direction decay, and find the minimizer of this function. And this defines the exact length search. Okay? Exact length search. For example, we can give a picture. This is a phi alpha, which is defined as fxk plus alpha dk minus fxk. Okay, when alpha equals 0, this phi 0 is equal to 0. Okay, so usually this will decrease until some point it will increase. Okay, it will increase because if you go along this direction, if you begin from xk and go along the descent direction, in the beginning the function value will decrease, but finally if you go further, you go very far away, the function value will increase. So this point is alpha k, which corresponding to the exact length search. Okay, so this point, or we can call it alpha bar. It's equals to the argmin of phi alpha. For alpha is greater than 0. Okay, so this is the explanation of the exact length search. Actually, there are several ways to implement the exact length search, but it is not very practical because it requires a lot of computation, like a lot of computation of the function values. Okay, in some sense it is very expensive, but it is useful. On the other hand, it is very useful for the convergence analysis to get some theoretical result. Okay, so we have some properties of the exact length search. The first is, if the alpha is determined by the exact length search, we have the phi prime alpha equals to 0, okay, because this phi is invariant function, okay, one variable function. So we can get the gradient, the grade of f at this point transpose dk equals 0. So if actually this is just the next iterate, xk plus 1. So we got the grade of xk plus 1 transpose dk equals 0. Okay, and the next is, if we assume the objective function f is convex and quadratic, for example, if you, which means you define the f is in this form, okay, then the alpha, which get from the exact length search, has this form, okay, has this form. Actually, how do we get this? You just substitute the gradient of f by the gradient of, by the gradient of this convex quadratic, okay? It's very easy. Actually, the reason why we consider about this convex quadratic is, for example, remember in the beginning we are considering this problem, okay? The linear system, we want to solve ax equals b, okay? Actually, this problem is equivalent to minimize this function. Okay, for example, if we assume that this a is positive definite, okay, positive definite. So, if a is positive definite, then this problem is convex and of course convex and quadratic. Actually, this is strongly convex. Okay, this is strongly convex. And the solution, for example, if we assume the x star is the solution of this problem, then we know the sufficient and the necessary condition of this problem is the gradient of f at x star, which is equal to 0, okay? And this is actually the ax star minus b equals 0. Sorry, this is x. and this is just the ax star equals to b. Okay, so if A is positive definite, so then the solution of this linear system is also the solution of this this quadratic optimization problem. Okay, just because of the necessary and the sufficient condition. So this is the reason why we usually consider about this convex quadratic when we consider, at the same time when we consider about the linear system. Okay, so this is one of the, another preliminary is about the definition of the conjugate vectors. So we see a set D0, D1 until DL is the conjugate with respect to a positive definite matrix A if for DI transpose A DJ equals 0. For all I does not equals to G, okay, for any different I and G. Okay, so a set of mutually orthogonal vectors is conjugate with respect to the identity. Okay, we can got this immediately. Okay, and if a set of vector is conjugate, then it is also linearly independent. Actually, you can get this property very easily just by checking the definition of the linear independence. Okay, so this is a definition of conjugate vector, a set which is conjugate, and we know if a set of vector is orthogonal, then it is conjugate. If a set is conjugate, then it is linear independent. Okay, so this is a preliminaries. Okay, now we go to the conjugate direction method. Okay. Okay, so we are still considering the linear system Ax equals to B. Okay, so how do we solve it? Before we go to solve it, we define the residual function, the residual vector of this linear system is Rk. Okay, the Rk actually it's R equals to Ax minus B. So Rk equals to Axk minus B. So Rk is a residue as upon Xk. Okay, so the conjugate direction method is like this. Actually, it's a kind of it's a special case of the linear line search scheme. So you get the next iterates by Xk plus step size times direction. Okay, and actually I should put the direction first. The direction D0 to dk are conjugate. Okay, are conjugate with respect to the matrix A here. Okay, or it with some other. Okay, it's a conjugate, and the alpha k is determined by this formula. Okay, actually, how do we get this? This is exactly get by the line search, exact line search. Okay, just to recall, what is exact line search? The exact line search is just to minimize this invariant function, phi alpha, and if you assume your function is quadratic, then you get this. Okay, then we implement this, the formula of this alpha, in the scheme of the conjugate direction method. Okay, so the conjugate direction method contains two parts. First, the direction are conjugate, and then the alpha k is determined by the exact line search. And actually, remember these problems is equivalent to minimize a convex quadratic function. Okay, then you use the exact line search for that minimization of that quadratic function. Then you get this. Okay. And the first result is it's a globalization of the conjugate direction method, but for the linear system, for solving the linear system, it says for any initial point, the sequence generated by the conjugate direction method converges to a solution x star of the linear system at the most n steps. which means it has a finite termination, okay? At a finite, it has a finite convergence. The proof is like this, okay? So first, since the decay is the directions are linearly independent, this is from our preliminaries, okay? Because decay, D0 to decay are conjugate, so they are independent, linearly independent. So we can rewrite the x star minus x star is a linear combination from D0 to Dn minus 1 because they are linearly independent. Okay, and then we multiply on both sides by this vector, okay, by this vector, and we use the property of we use the vector from the D0 to dk minus Dn minus 1 is conjugate. Actually, this dk is some vector among D0 to Dn minus 1. It's one of them, okay? And then you can get sigma k equals to this formula, okay, to this term. Actually, you multiply both sides by this dk transpose A, and then you use the conjugates property on the right side of this relation. Then you get this. Okay. So we get another relation from the definition of the conjugate direction method. Okay. Since xk is generated by the conjugate direction method, so then you have xk plus 1 equals to xk minus alpha k dk. So you rewrite it until the x0. You get xk equals x0 plus alpha 0 d0 until alpha k1 dk1. Okay, and then we also multiply the dk transpose A on both sides and use the conjugates property on the right side. Okay, then you get this property. Okay, the dk transpose axk minus x0 equals to 0. Okay, from this property we get this should be dk. Okay, the dk transpose Ax minus x0 equals to actually you can minus xk and plus xk here. Okay, you minus xk and plus xk in this bracket. Okay, and you use this equality. They use this equality. Then you get this equals to x star minus xk, and this equals to the dk transpose the pk. Okay, pk transpose b. Actually, this a times the x star is just the b because x star is a solution. Okay, so this equals to bk transpose b minus axk. Okay, then by the definition of the residue here, we use the residue. This b minus axk is just the minus residue, so this equals to minus dk transpose rk. Sorry for the typo. The pk, this 3 pk should be dk. Okay, so then we have the sigma k equals to this term. Okay, to this term. This sigma k is get from this formula. Okay, this formula we get from the decay. The direction decay are linearly independent. So we know the sigma k. No, there is no sigma here. Sigma k equals this, and from the decay, from the xk is generated as a conjugate direction method. We got this dk transpose Ax star minus x0 is equal to this term. You have a minus here, and just this is just the definition of the alpha k in the conjugate direction method. So we get the sigma k is equals to alpha k. Okay, sigma k and equals alpha k, and we can see the definition of the xk. sk is equals to x0 plus alpha 0 blah, 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 alpha until alpha k minus 1. And the x star also equals to x0 minus a. If we get the alpha k or alpha k minus 1 equals to sigma n minus 1, then we get this xk is exactly the x star. So we know until some k's iterate, the xk will equals the x star. Then it will converge with the finite iterations. Okay, so this is the first property of the conjugate direction method. Okay, it converges with finite iterates, and at most n steps. This is the dimension of the problem. Okay, so we go to the next property of the conjugate direction method. For any initial point x star x0, if we for any initial point, we suppose xk is generated by the conjugate direction method. Okay, then we know the residue is orthogonal for all the previous directions, okay, is orthogonal to the di, which I from 0 to k minus 1. And the xk is a minimizer of this quadratic function over this subspaces, okay, over these subspaces. And this subspaces is xk plus the span subspaces by x0 until xk minus 1. Actually, this is a very important result for the conjugate direction method, which we will the conjugate gradient method will also preserve this property. But now we will first discuss for the more general one, because for the conjugate direction method, we do not know how do we compute or how we construct the direction. Okay, we just know they are conjugate. Okay, they are conjugate with respect to the matrix A, but we do not know how to compute it. But in the conjugate gradient method, you will have a specific formula to compute of the direction in each iteration. Okay, so the idea of the proof about this theorem is, first we prove a point x tilde, okay, is a minimizer of the function phi over the set if and only if this the residue of at point x tilde transpose di equals 0. Okay, equals 0, and for any I from 0 to k minus 1, and then we use induction to show that rk, okay, that this rk, which is a residue at the point xk, is orthogonal to all the previous direction. And then from the first point, we got that xk is a minimizer of this quadratic over this subspaces. Okay. So first we define this h sigma, which equals to this phi at this point. Okay, and the sigma is the pair of it's a vector consists of sigma 0 to sigma k minus 1. Okay, so we know since this h sigma is strictly convex quadratic, so it has a unique minimizer, which is, we call it sigma star. Okay, so the partial h at the sigma over the partial sigma I equals 0 for any I equals to 0 to k minus 1. Okay, so with this by the chain rule, this relation means the phi x0 plus sigma 0 star until sigma k star dk transpose di equals 0. Okay, and since the gradient, the grade phi x equals to the ax minus b, which is just the residue. Okay, so we have the minimizer, the x theta equals to this. Okay, this is a minimizer. Okay, this is a minimizer, and sorry, you have there is a grade here. Okay, you have the grade. The grade this here you have the grade phi at this point interproduct with di. Okay, with di. This is a chain rule. Okay, so from this chain rule, from the optimality condition, we got this, and from this relation by the chain rule, we got this one. We got at the residue at point x tilde k transpose d pi. This should be di. Okay, any previous direction equals 0. Okay, equals 0. Okay. So now we use induction to show that the residue of xk, rk transpose di equals 0 for all I from 0 to k minus 1. Okay, the idea is the first we consider k equals to 1. Okay, so we have the fact that xk equals to x0 plus alpha d0. Actually, this is exactly the minimizer of phi along the d0 because the alpha is the alpha 0 is from the exact length search. Okay, and of course you can check this just by the very simple computation. Okay, you can get it with in two ways. Okay, so next we suppose this rk minus 1 transpose di equals 0 for all I equals to 0 to k minus 2. Okay, so for k rk, it's equals to, by the definition, it equals to ax minus b, and we can substitute xk equals xk by the definition of the conjugate direction. Okay, so the xk equals to the xk minus 1 plus alpha k minus 1 dk minus 1 minus b. Okay, and by the definition, this axk minus 1 minus b is just a residue at a point xk minus 1. So this is rk minus 1 plus this, the middle term. Okay, the a alpha k minus 1 dk minus 1. Okay, so we consider about the dk minus 1 transpose rk. Okay, this dk minus 1 transpose rk, just by we substitute the rk by this rk minus 1 plus alpha k minus 1 a dk minus 1. So we got the first equality. Okay, and then we keep the first term the same, and we use the definition of the alpha k minus 1, which is get from the exact length search for a convex quadratic. So we have this. We substitute the alpha k minus 1 by the formula of the exact length search. So we got the second inequality, and so this equals 0. So we have shown that for k minus 1, this dk minus 1 transpose rk equals to 0. Okay, and so meanwhile, for any other vectors, for any other vector di, which I equals to 0 to k minus 2, the di transpose rk is just equals to these terms. Okay, these terms, and we substitute rk minus 1 by this relation. Remember, the rk can equals to rk minus 1 plus alpha k minus 1 a dk minus 1. Okay, so we use that expression of rk here. So this di transpose rk equals to this term. And we know this term, okay, the second term equals 0 because the di are conjugate, okay? The the d0 to dk minus 1 are conjugate with respect to a. And the first term is equal to 0. We have proved in the last slide, okay? So we got this equals to 0, okay? This term equals to 0. And we got this equals to 0, okay? This equals to 0. And this equals to 0 because of the induction hypothesis, okay? Induction hypothesis. Okay, so finally what we get? We have shown that the rk transpose di for I equals to 0 to k minus 1 is equal 0. So we finish this proof, okay? And we just review a little bit the result. So we see that the xk is generated by the conjugate direction method, okay? So first we have that all the residual at xk are orthogonal to all previous direction, and also the xk is the minimizer of this convex quadratic over these subspaces. Okay, the idea is that you prove that the minimizer of the phi over this subspace is equivalent to this orthogonal property, and then you use induction to prove the first condition hold. Okay. So this is the second property of the conjugate direction method. Okay. Next, we will go to the conjugate gradient method. All the discussion above are based on any choice of the conjugate direction. Okay. We just assume all this set is this vector set is conjugate with respect to A, but we do not know how to determine it. For instance, we can use the eigenvectors of the set A. For example, V1 to Vn, which are mutually orthogonal to each other, or mutually orthogonal. So it is also conjugate with respect to A. So this is one of the options. But if the dimension of the problem becomes very large, then the computation of these eigenvectors is very expensive. So this is not a wise option. And another is we can use the kind of modification of the Graham-Schwarz orthogonalization process. But this kind of orthogonal process requires you restore all the vectors you generated in this process. So it requires a big amount of the space to restore your vectors. So is there a way we do not need to store so many vectors, and also which is cheaper to compute the next direction, which gives us conjugate gradient method, okay? So what we want to compute the new direction dk just using the previous one, okay? Just using the dk and the current, like the current gradient or the current information. So it does not need to, we do not need to know all the previous elements like d0, d1, dk, because if your algorithms goes many iterates, okay? If, for example, if you add the 10 to the power of 5 iterates, if you need to restore all the previous direction, it requires a lot of space to restore them. And as your iterates go ahead, you require more space, okay? And another good thing is the decay is automatically conjugate to these vectors. We mean all the previous one. So we want to compute the decay just by the current information and the previous one, which is cheaper, and it can be automatically conjugated to the previous one, which satisfies the definition of the conjugated direction method. Okay, so the direction is defined by this. Decay equals to, first you have the minus RK, which is a current residue, and some beta k times the previous direction. And we can see by this direction the decay can be automatically conjugated to all the previous decays. Okay? And the beta k is determined by the requirement of dk minus 1 and the dk must be conjugate minus a. Okay? So you just multiply dk minus 1 transpose a on both sides of this relation, and by dk and the dk minus 1 are conjugate, then you can get the definition of the beta k very easily. So this definition of dk and the formula of beta k consists of the definition of the direction of the conjugated gradient method. Okay, so this is a theoretical version or preliminary version of the conjugate gradient method. Okay, so first you have the initial point. Okay, and you have the R0 and you have the initial residue, and you have the initial direction, which is a minus residue. Okay, then you compute the the direction, the step size, which is just by the exact line search. Okay, and then you go to the next point. Okay, xk plus 1. Since you have the next point, you can calculate the next residue. Since you have the next residue, you can calculate the beta k. Sorry, this is a beta k minus 1, beta k plus 1. Since you have the beta k plus 1, you can compute the next direction of the conjugate gradient method just by the negative residue and beta k plus 1 minus dk, the last direction. Then you can go to the next iterates. So this is the definition of the conjugate gradient method. And be careful. This conjugate gradient method is for solving the linear system. So we call it the linear conjugate gradient method with exact line search. Okay, of course with the exact line search. For this algorithm, we have this very important property. So if we assume that at case iterates, which generated as a conjugate gradient method, linear conjugate gradient method, which xk is not the solution. So you have the four important properties. Okay, you see you also have this orthogonal property, but among the residues. Okay, and you have this subspace properties among the residues or among the directions, and then you also have the conjugate property about the direction. Okay, so in the next class we will discuss about the proof of this theorem, and then we'll go to the nonlinear conjugate gradient method. Because actually this conjugate gradient method was proposed like more than 70 years ago for solving the linear system with positive definite matrix. But later people found for minimizing a nonlinear convex function, the conjugate gradient method is also efficient. So later we will introduce the nonlinear conjugate gradient method. So this is all the